Alright, welcome to our next video here. In this video we're going to essentially review some assembly instructions and a couple of concepts that go along with that. So my goal or my hope is that this is by and large a review for most of you. However, if it's been a little while since you've done any assembly programming or looked at any assembly instructions, it'll probably be worthwhile to watch through the rest of this video here. What you'll find is that it's not too hard, it's not too challenging to get used to working with IDAPRO. What you will run into and what will be the most challenging then is understanding the things that IDAPRO is telling you, the assembly, the instructions in order to understand the program that you're analyzing. So that's why we're going to review this. We'll also get into the IA lab again, and we'll just look at a sample, a very simple sample program. Again, encourage you to follow along and do the same with it. I do that for a variety of reasons. One is just to look at some of these simple instructions. Two is also to show you how I build the programs, compile the programs using the Visual Studio developer tools, the command line, in the VM or in a Windows machine, just so you've got that background and that insight as well. So to begin, I want to talk a little bit more about main memory, and this is going to be kind of a common theme here throughout most of the course, is memory and how it's important to understand that when a program is executed, it's loaded, it's mapped into memory, and that's where it's executed. It's not reading the data off the disk anymore. It's loaded into memory, and that's where it's reading it. We have something called virtual address space, and we'll talk a little bit more detail about that here down the road. What that virtual address space here, it's being represented graphically through this capture, this screen capture, this image on the right, and that we're largely dealing with 32-bit machines. You know, if we were to do a 64-bit, you would just change it to 64-bit, right? But we're going to stick with 32-bit for now. And so with 32-bit, we have 32 bits of addressable space. That's the limitation that you run into in the 32-bit arena, is the number of addresses, the addresses that you can provide addresses to. High address, low address. We talk with 32 bits, talk about 32 bits. So high addresses start as an x86 hex digit number. So FF, 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 FF. The low address then, all zeros. And because 32 bits is 4 bytes, that's 8 hex digits, that's 8 hex characters, that's where those addresses are coming from. So in the previous video, when we turned on the line numbers inside IDAPRO, that's why we were looking at those, or that's why those addresses appeared the way they did. 00401001, or something along those lines, right? That's the address. That's the virtual address that IDA has mapped. It's behaved a lot like an operating system and how it's loaded that file. In that address space, then, everything gets mapped to generally these locations that we're dealing with here. So we've got data, and you can see that it's somewhere in the address space. It's not always going to be in these exact locations. That's going to depend on how it was built, how it's mapped into memory, and some other variables. But so generally, we have places for data. We have addresses, or a region of addresses for data. We have a region of addresses for code, or the text section, and we're going to get into more detail about this when we parse the PE format, which is another reason we do that, hopefully to help provide some better and deeper understanding as to how this works. We have the heap, which is dynamically allocated memory, and the stack, which is going to be for the control flow of the program, as well as local variables and function arguments. And generally in memory then, we have the heap and the stack is going to grow down, and the heap is going to grow up in this address space. That means that the stack is going to go from a higher address to a lower address. The heap is going to go from a lower address to a higher address, and this maximizes, based on how they grow, this maximizes the space that they have available for each construct, for the stack and the heap. We'll talk in detail about the stack here throughout the semester, and just kind of refreshing as well as introducing some additional concepts there. But keep in mind, it's very important to understand that the stack grows to a lower address. And so you're going to want to be able to recognize that and understand that when we're analyzing programs, whether statically or dynamically. Okay, so that's just kind of some big picture, talk a little bit more about memory and how a program is structured. The other thing I wanted to mention before we get into some of the specifics here is opcodes and endianness. And so remember, endianness can be or have an impact on the analysis that we're doing. That is, what order are the bytes stored? So big endian, you're going to see that the most significant byte is first, and little endian, you'll see that the least significant byte is first. And so just keep that in mind, because oftentimes as we're looking at a program inside IDA, if you're looking at data, it might be in big or little endian. It just depends. And so you might need to take a look at that. You might need to restructure the byte order in order to have the data make better sense or more sense. Opcodes. Opcodes are the actual, essentially the binary representation of the instruction. When we talk about binary, we talk about a program is just binary written to disk. It's binary that gets loaded into memory and executed. And that binary is organized essentially into these bytes. And these bytes we can see are the opcodes. And so the opcode 55 is push EBP. The opcode 8BEC is move EBP ESP. The opcode 81 is 81EC is sub ESP, and then 3C010000 is the data, 13C hex, right? And you'll notice that that's in little endian. Least significant byte is first, based off of this display here. Okay, so opcodes are important to understand, not so much right now as we're going to focus more on the instructions themselves and trying to understand the functionality of the program. But when we get into shellcode, we'll talk a little bit about shellcode and exploitation, then we'll definitely be working with opcodes a little bit more detail. Okay, so that's what an opcode is, and you can see here an example of the endianness of this data having an impact on how we interpret it. IDA Pro interpreted it correctly. It detected the endianness, displayed it as 13C, right? 13C. You can see those bytes are a little endian, right? Least significant, most significant. Okay. So we've got operands and registers. So when it comes to an instruction, then not all instructions have operands. Operands, you think of those as arguments, but a lot of them do. And they'll have a single or they'll have two different operands. So a move instruction, for example, has two operands. We have move the destination, comma, the source. So move into EAX 8, the value 8, or move into EAX, the value in EBX, right? We have two operands. A call instruction has one. We have call and then the address that we want to move into EIP. So, call and then an address, or call printf. Jump would have no operands. If you just have an unconditional jump, the JMP instruction, that's just going to jump to that address. So data used by an instruction, the data that you can see in those operands will be immediate, so a fixed value. So move into EAX 0. You can have a register, move into EAX EBX, and then you can also have a memory address. And so we looked at that as an example in the previous video where we had that D word underscore and then an address, right? Move into EAX, move into a register, data from a memory location, a memory address. And so those are the different types of operands. The registers, okay, so we generally are going to focus on these. These are the main registers that we'll be dealing with throughout the course. Not all, but these are the main ones. We have the general purpose, EAX, EBX, ECX, EDX. We have stack related, EBP, ESP. We have ESI and EDI, which are used generally for data transfer. So ESI is the source, EDI is the destination. There's segment registers. We won't talk a ton about those. We will cover a little bit in FS kind of as we go throughout the course. We have the status register, E flags, and then we have the instruction pointer, EIP. Within these registers themselves, the general purpose, EAX generally is the accumulator. That is, when a function returns, if it returns a value, generally it's going to be put into EAX. And so when you look at a function call, you want to look for, okay, after that instruction, call some function, is the register EAX used after that function call? Because if it is, maybe you see a call, some function, and then you see stack cleanup, and then you see move into EBX, EAX. Then what we're looking for is a function that likely returned a value, and that value, EAX, got moved into another location, another register, or maybe a memory address. ECX generally used for your counter. So if you see a loop, you're looking at a loop, then if you're trying to determine maybe how many iterations that loop is going to have, you want to be looking for the use of ECX, because likely that's going to be used for the number of loops. For I equals 0, ECX is going to be I in that case. Okay, E flags. And with these registers and the flags registers, right, to jump to a 64-bit world, it's not that much of a leap. 64-bit has more registers. All the registers, instead of being 32 bits, are now 64 bits. So not too much different there. Okay, E-flags, it is a 32-bit register. Each bit is a flag. So there are 32 flags then inside of the E-flags register. The flags, we likely won't have a reason or occasion to directly use the E-flags register. But what we will use it for, or what we will see, is that maybe there's a comparison that's done, and then a test or a compare, in which case we know, or we need to understand, that that comparison is looking at certain flags within E-flags in order to determine whether or not to jump, in the case of a conditional jump. So after certain operations, after certain instructions, the zero flag, the carry flag, the sign flag, the trap flag, certain flags can be set. And we just need to be able to understand or be able to look up, after an instruction, what flag is being checked if we care. Okay, static analysis, not as important maybe. With dynamic analysis, possibly, because with dynamic analysis we can change those flag registers, as we're stepping through a program. So, okay, EIP is a big one. EIP is the register that controls the flow of the program. So EIP, 32-bit world, 32-bit register, we're going to have the address of the next instruction to execute, or the instruction to execute is in EIP. And so EIP will just sequentially start executing instructions in a program unless an instruction changes that value. A call instruction does that, right? And there are only a few instructions that will change the value of EIP. So call is one. We call and then a location, and that actually moves into EIP the address of that function. So this is going to control the flow of the program. When we get to the later half of the semester, we're going to look at Stack Overflows and maybe even get into return-oriented programming a little bit. And what we're dealing with there essentially is memory corruption as well as our ability to take over EIP. If we can control the data that goes into EIP, not directly, indirectly, then we can control the flow of the program. We can hijack it, we can exploit it. Okay, a lot of simple instructions. I already talked about move a little bit, and move is very simple. It moves data from one location to another. And so it has two operands. We have the move instruction itself. The two operands then are going to be the destination and the source. So we're going to move into an address from an address. So from a register to a register, from memory to a register, from memory into a register. That's what the move instruction does. Okay, LEA, load effective address. I just spent a little bit more time going through an example here because not sure how much you cover LEA in 314. I know that I cover it a little bit more in detail now, but not sure everybody else does. So anyways, I just wanted to point out how load effective address works. So LEA, load effective address, it's similar to move in that we have two operands. We have a destination and a source. So here you can see the format, LEA, destination, and source. And what LEA is doing is it's moving an address into that destination, moving an address. Okay, you'll notice that there are certain times that we need an address. We don't need the data, or we need to calculate an address. We can't calculate the data, and LEA will allow us to do that. So in this example, whatever values in EBX plus 8 are moving that address into EAX. And throughout the programs that we're going to look at, the labs and such what we'll look at, you'll see that LEA gets used quite a bit. Think address. Every time you see LEA, think, okay, in EAX right now is an address. It's an address to something, a control structure, a data structure, data. It's a pointer. So that's what you want to be able to see. Now, if you look down below, I have two screen captures, and this is our 314 environment, or at least it was. And the little, like 3 or 4 different examples here. A is a label. It points to data that I defined up above here that you can't see. So if I move into EAX A and dump registers, what we're looking at right here is the value of A. So EAX equals, and you can see 8049A58, right? That's an address, 32-bit address. 1, 2, 3, 4, 5, 6, 7, 8. 8 hex digits, that's 4 bytes, 32 bits. Okay, so that's an address. Okay, if we put brackets around that, that dereferences that value. So A points to an address, putting brackets around it dereferences it. So this next dump registers, we moved into EBX, that dereferenced pointer, the data. So if we look at this next, you can see that it is the value bad code, BADC0DE. Okay. Now if I do LEA ECX, put brackets around it. You have to put brackets around it. What that's moving into ECX isn't the dereferenced value, it's the address. So if we look at dump regs, the next dump regs, in ECX, 8049858, the same value that we have in EAX, the actual address for that data. Okay, and now you can do things like calculate. So let's say that I want to calculate a plus 1. Well, what is the address for that? LEA into EDX, dump regs 3. Okay, now you can see in EDX, 8049A59. A is at A58, plus 1, A59. So that allows us to calculate those addresses. So that's what LEA is doing. It's giving us addresses. Okay, arithmetic should be relatively straightforward. Addition, subtraction, multiplication, division. We have some logical operations. We'll see those, and we'll talk a little bit more about those here. Just recall that where the number of registers that instruction uses, some operations use more than one register. If you're multiplying EAX, EBX, then it's going to store the result, because we're using two 32-bit registers. It's going to store those results across EDX, EAX. If we did 16-bit, then it would be DX, AX, and if we did just 8 bits, I think it would be, gosh, I can't remember now, probably, I'm drawing a blank. So anyways, hopefully you get the idea, right? That a multiplication, some arithmetic operations store the results across more than one register. Division, okay, stores the remainder in EDX and the result is in EAX. So while the instructions themselves are relatively straightforward, we divide and we have, two values or two operands. Where the results are stored, you just need to make sure that you understand that, because you'll see a lot of division instructions, and then the results after that division, what's being used? The remainder or the result, right? If just the remainder is being used, then maybe it's not division, maybe it's modulus, right? So some things to keep in mind. Okay, logical operators, OR and XOR. Again, you'll see those quite a bit. Just remember those bitwise operations. And again, should have covered those in 314. So if anything seems a little rusty, certainly let me know. I can point you to, I can provide additional video. I can provide you additional resources, such as the 314 videos for review, as well as some of the material, the PDF and stuff in 314, just to help with that. So XOR, EAX, EAX, if you XOR a register with itself, that's the exclusive OR, then each bit, right, these operations work at a bit level. And so each bit is going to be XORed. And the only time, so like with the XOR operation, the only time the result is 1 is if they're different. If they're the same, then we have 0. So if they're the same, so if we XOR EAX and it's all 1s, so XOR 1 1 1 1 1, etc. against 1 1 1 1 1, they're not different. So the result's going to be 0. So the result of an XOR, EAX, EAX, a register against itself, is to zero out that register. So that would zero that out. Or an AND, right? So just remembering those logical operations and realizing the result of that logical operation is stored in this destination operand. Okay, shift operations, shift right, shift left, those work at the bit level as well. And so you can see here as an example, move into EAX, FF, FF. So if we look at this dump, we can see there's EAX, and we have the lower 16 bits of that register, FF. I zeroed out the upper 16 bits. Okay, shift left EAX, 16. So that's shifting it 16 bits, right? And now if we look at that next register dump, we can see that it's moved 16 bits, right? 32-bit register, so it makes sense that if we moved from the lower 16, or if we were occupying the lower 16, and we shifted 16, that we moved to the upper 16, right? And you can see that there. The last one, shift left EAX1. Okay, now we can see that we shifted, right, all of these bits, and now that particular hex digit, that nibble, that 4 bytes or 4 bits right here, is now an E, right? Because this F represents, each hex digit represents 4 bits. So 1111, 1111, 1111. This was 1111, but we shifted it to the left 1 bit. So now it's 1110, so which is 15, or E in hex. Right? So that's how shift left, shift right is the same. It just shifts to the other. It shifts the other direction. And then there's some rotate instructions as well, which you'll see here as as we get to the next slide. And that the rotates shift the bits back on. So here you can see using EAX, F is here, then it's rotated here, and now it's being rotated where some of the bits start to rotate back on to the end of that register. So now it's spread across kind of from this end to this end. Okay, so rotate right, rotate left works in the same fashion, and that the bits are just rotated around. All right, the last thing, the NOP does nothing. It's like an exchange EAX. In fact, I think it is an exchange EAX. Opcode 90. And it's often used in a NOP sled, and we'll create some NOP sleds here towards the course when we do dynamic analysis for our buffer overflow attacks. So does nothing. It's just like you saw there, exchange EX, it does nothing. So, all right, anyways, I'm hoping that was by and large a review from 314. Again, any questions, let me know so that we can discuss those or provide resources, provide more videos. All right, oh, sorry, open. Couple of just real quick examples. So I've already got IDA open, and a couple things I want to point out here now is generally how I'm going to build most of our programs that we're going to look at. So in this case, you can see I've got Sublime Text open, which is my text editor of choice and the one that I have by default in the VM, and you're free to choose whichever one you like. I created just a really simple C program. So I've got standard io.h included here, and then main. Inside of main, there's one local variable, sum equals 1 plus 2, and then return 0. So you see it really doesn't do anything. In order to compile that, we'll use Visual Studio. I'll use Visual Studio. And so if you look under your programs, you'll find Visual Studio 2015. And if you scroll down, you'll see the developer command prompt for Visual Studio 2015. Okay, this is not the same as your normal command prompt. So if you open up Start menu and you open up command.exe, CL is the program that we're going to execute to compile, and you're going to see that it's going to say, I don't know what that is. Okay, but under the developer command prompt, CL will tell you, here's your usage information. Okay, so that's what we're going to be doing. Now, when this opens by default, it drops you into the Visual Studio directory. So from there, you know, your basic CD commands to navigate to wherever you need to go. So in this particular window here, I've already done that. Okay, in order to compile, pretty straightforward. CL and then the source file. So CL sample.c. And you want to look here to make sure that you didn't get any errors. And if you get an executable, then you didn't have any errors. That doesn't mean you don't have warnings, right? Warnings can still generate, means that something's not quite right, or there may be a problem in your program under certain situations, but it was still able to compile it. The other thing that you'll get with Microsoft is you'll get this object file. And let's see, here it is right here, sample.object. So that's the binary, that's in a specific file format. We generally don't deal with the objects just because as a reverse engineer, you generally don't have the source, you generally don't have those object files. All that needs to be done from this object file is the linking, and now you'll get an executable. And this is, I know I've been saying this a lot, there are, that's another concept we'll talk about here throughout the course. So you'll see that there are just a lot of pieces that we got to connect here to really, what I hope, get a good solid understanding of this process. So we'll do a little bit with that later on, but it's going to generate with Microsoft, you're going to get that object file, and then you're also going to get your executable. And this, of course, is what you would execute. So a little bit different than GCC. GCC, generally, you don't get that intermediate object file produced, or you don't see it by default. Okay, from there, you can take your executable, you can drop it on IDA, and it'll open it up. And I already went ahead and did that. So here you can see this is the program. Now, this is the default location that IDA is dropping us, and this is not where we want to start. And so there's a lot of stuff going on in here, and a lot of this is just set up and built up for the program, exception handlers and some other things. And so what we want to do is we want to go down and jump to this location, 401.260. Okay, so when I talk about and have talked about how sometimes it's hard to know exactly where to go, yeah, it depends on how a program is compiled. I'll try to make this as easy and as painless as possible so that you don't have to get lost anywhere, or if it's not as straightforward as it could be, to tell you exactly how to get there. But you'll also pick up the knack as we go through the course. So anyways, it can be kind of painful to figure it out, but I don't intend to do that with any of the labs. So anyways, this is main. So if we go back to that source, sum equals 1 plus 2 returns 0, this is that code. And you can see that after we compile the program, this is what the compiler did to it. What I want to point out here, I think, is interesting, and that we have var4. Okay, I said, and we've been talking a little bit about the stack. var4 is space on the stack, right? We have a local variable int sum, so that var4 is space that's been allocated for that variable. So because we have the source, if we hit the N key, we could rename that. We could say that that's sum. Okay. Here we have push EBP, move EBP ESP, push ECX. So that's prolog type stuff. Next thing you can see, we have move into sum, the value of 3. Right? Sum equals 1 plus 2. So the compiler recognized that, and it did a little bit of optimization for us and said, no, I don't need to do 1 plus 2, don't need to do any sort of arithmetic. All I need to do is move 3 into sum. Right? And so here's an example of not only something called optimizations. Compilers will do that. They will find ways to make the code more efficient. But then it's also an example of the move command. We're moving into this location, a place on the stack, the value 3. Okay, then we have XOR EAX EAX, move into EBP ESP, pop EBP. So this is epilogue, this is prologue. And what do you think XOR EAX EAX is? Well, what do we return? Return 0. What does XOR do when you use the same source and destination? Zero something out. So XOR EAX EAX is zeroing out EAX. EAX is generally the register we use to return data from a function. We're getting ready to return from our main method. So it's zeroing out for that return 0. So that's what that's doing. Okay, and then we return. Okay, we could do another additional example. We could say int a equals 0, int b equals 3, and maybe now I do sum equals a plus b. I'll save that, go back to the command prompt, I'll minimize this, compile that again, and I will open it again. All right, so now IDA will take that file, it'll build another database. Because I use the same name though, it's asking me what do I want to do. Do I want to load existing, because I've already got one open? Do I want to overwrite, because it's a database with the same name, or do I just simply want to cancel? So in this case, I'll go back and I'll just close IDA, and I'll just allow it to overwrite. Because if it doesn't overwrite, it's not going to be this newer version, this more recent version of the program that I just compiled. Okay, this takes just a second, so hang tight as this IDA does its analysis. While we're waiting, so one thing that you could do, and I again highly recommend, highly encourage, is to do this with some programs. Write some programs, write some simple programs in C, compile them using the developer tools, and then open them up in IDA and see what this looks like. You talk to a lot of people that get into this field, reverse engineering and malware analysis, and that's where they start. Those are some of the things they do, is they start with basic programs, compile them, disassemble them, see what they look like, analyze them in IDA, and that's a really good practice that I think will really help in understanding and preparing you for the labs and just to become really proficient in this field if that's what you want to do. Okay, IDA's done, back to an idle state. We can see that down here in the lower left. So we'll scroll down to about here, and we'll double click on this instruction. Double click will jump us to that. Okay, here we can see more local variables. Okay, we go back to that original source, sum A and B. Right, now we have 3 local variables. With the source file, which is what you're going to be doing with Lab 1, you're going to have the source file to build off of. We can try to figure out which one's which. right? Sum is 3. So var C, we could rename that one sum. So hit N and rename it. If we look at A is 0, okay, so if we have a move into a location on the stack, a value of 0, then we know that's our variable A. So hit the shortcut key N, rename that one. 3 into var 8. Okay, so let's rename that one B. And now we've added what we, especially because we have the source, we've made this database a little bit easier to read because we have sum, A, and B. Okay, you'll also notice the order that these are in. Sum, A, and B, sum, B, and then A. Right? It's up to the compiler to determine. They're not always in the same order. Let me see, make sure I did that right. Yeah, okay. All right, and you can see moves, right? Moves are into those locations. We move into EAX-A. We add the value in EAX with B, right? What did we move into EAX before the add? Well, we moved into EAX-A. So that gives us the result of that addition, and it leaves the result in EAX. So now we move into sum, the value of EAX, right? And that's how we're starting to map this program in C to these assembly instructions. Okay, another thing that you'll notice, and this is really helpful, is that when you select a register, when you select a value, IDA highlights it for you. So when we're looking at, let's say, this add, and I want to say, okay, add EAX EBP plus B. Well, what was an EAX? Because I need to know that in order to understand what's being added. If I highlight that, we can trace that backwards and say, okay, the next instruction that uses EAX is right here. And into EAX, we moved EBP plus A. Okay, well, what is EBP plus A? Well, we highlight that, and we can see it's not the most immediate previous instruction, it's the one before it. So EBP plus A, we moved into that 0. So now we know, back to this original question that we had, what was in EAX, we know it's 0. We can do the same with B. Okay, B is here, we have a value of 3. So now we know when this instruction is executed, we're adding 0 plus 3, and then we're moving 3 into sum. So, okay, well, that was just an example, and again, hopefully enough to get you started to kind of play around with this on your own. We'll talk about the first exercise, which will help, and then the first lab, which will be very similar here, and then I'm going to give you the source. You'll have the lab 1 file, and you're going to go through and rename and label in IDA that particular database. So again, we'll continue to do exercises, we'll continue to do examples just to help reinforce and kind of solidify these concepts that we're talking about. So with that, that's all I have for this video, and I will talk to you guys in the next one.